A profound crisis is unfolding in our understanding of the cosmos, and the ultimate destiny of everything that exists hangs in the balance. Since 1929, humanity has understood that we inhabit an ever-expanding universe, a revelation first demonstrated by Edwin Hubble, who proved that galaxies continuously drift farther apart with each passing moment. This fundamental expansion has become the cornerstone of our entire framework for understanding cosmic evolution, spanning from the Big Bang's primordial explosion to the intricate formation of galactic structures across billions of years. At the heart of this cosmic puzzle lies a critical measurement: the rate at which the universe expands. This value, now universally recognized as a Hubble constant, was once considered firmly established. Today, however, astronomers find themselves grappling with unsettling uncertainty. Are we witnessing the dawn of a revolutionary shift in cosmology? Or have we constructed our entire model of universal mechanics on faulty foundations? I'm Alex McColgan, and you're watching Astrum. Come with me as we delve into the crisis shaking the foundations of cosmology, uncovering how Hubble's most celebrated discovery has transformed into one of contemporary science's most perplexing enigmas. Throughout most of human civilization, our conception of the universe remained remarkably small. Ancient societies envisioned Earth as a flat expanse crowned by a celestial dome studded with stars. The sun and moon traced their daily arcs across the sky, while constellations wheeled overhead in their eternal dance. By the 2nd century, astronomers like Claudius Ptolemy had conceived a geocentric model placing Earth immovably at the center, with the sun, moon, planets, and stars all revolving around our world. This paradigm would dominate human thought for over a millennium, enduring until the 1500s when Nicholas Copernicus revolutionized astronomy by proposing a heliocentric system, a radical concept positioning Earth as merely one of several planets orbiting the sun. Advancing to the 18th century, William Herschel charted numerous stars throughout our galaxy, the Milky Way, revealing it as a massive disc-shaped stellar system. Though it sounds archaic today, astronomers engaged in heated debates about whether the Milky Way constituted the entire universe or represented just one island galaxy among many scattered throughout a far vaster cosmos. This question found its definitive answer in 1923, when Edwin Hubble settled the matter conclusively. Observing through the 100-inch Hooker telescope at California's Mount Wilson Observatory, then the world's most powerful telescope, Hubble successfully distinguished individual stars within Andromeda, including his first Cepheid variable star. Employing Leavitt's law, named for Henrietta Leavitt, who discovered over 2,400 variable stars and demonstrated their utility for measuring cosmic distances, Hubble calculated that Andromeda lay approximately 900,000 light-years from Earth, a breathtaking expanse. This distance proved far too great for Andromeda to belong to the Milky Way, definitively establishing that separate galaxies containing their own stellar populations existed beyond our own. In a single stroke, Hubble expanded humanity's conception of the universe immeasurably, yet his groundbreaking work had only just begun. He proceeded to apply Leavitt's law to identify 23 additional galaxies and measure their distances, with some located as far as 20 million light-years from our planet. Eventually, Hubble concluded that millions upon millions of other galaxies must populate the cosmos beyond our own, permanently transforming the field of astronomy. However, Hubble's next revolutionary breakthrough also depended on the pioneering work of Vesto Slipher, an astronomer born on an Indiana farm in 1875. After joining the Lowell Observatory in Flagstaff, Arizona in 1901, Slipher conducted systematic observations of more than 40 spiral galaxies between 1912 and 1925. Scientists of that era understood that light from distant galaxies could be separated into its component wavelengths, creating spectral patterns that vary depending on which elements were present in the light source. Crucially, if the observed object was receding from us, those same characteristic patterns would appear shifted toward the spectrum's red end, a phenomenon we call redshift. Through years of meticulous observation, Slipher discovered that nearly every galaxy appeared to be moving away from our position. However, at that time, he lacked methods to measure precise distances to these remote celestial bodies, much less calculate their velocities accurately. In 1927, Belgian scientist Georges Lemaitre proposed a theory suggesting the universe appeared identical in all directions, and if Einstein's theory of relativity held true, must also be expanding. Unfortunately, lacking supporting evidence, his theory received little attention and was largely dismissed. That situation changed dramatically when Hubble re-entered the picture. Like most scientists of his era, Hubble remained unaware of Lemaitre's theory or of a similar one proposed years earlier by Soviet scientist Alexander Friedman. Instead, from his vantage point at the Mount Wilson Observatory, Hubble replicated Slipher's observation. Galaxies indeed seemed to be receding from us. But he noticed something unprecedented that had escaped everyone else's attention. Galaxies located farther away exhibited greater redshift, meaning they were racing away from us at higher velocities. Moreover, this pattern held true in every direction he observed. Additional observations revealed that virtually all galaxies appear to be moving away from one another, and remarkably, a galaxy's redshift correlated directly with its distance from Earth. This represented a monumental breakthrough. It could only mean one thing. The universe itself must be expanding. Hubble announced this discovery in 1929, and following its publication, it provided crucial supporting evidence for Lemaitre's expanding universe theory, which would eventually become known as the Big Bang. Hubble's original measurement of the universe's expansion rate, which would be designated the Hubble constant, came to roughly 160 kilometers per second per million light years, approximately 500 kilometers per second per megaparsec. However, this figure proved inaccurate, and even Hubble himself devoted considerable effort to refining it throughout his career. Since those early days, the Hubble constant has evolved into a fundamental cornerstone of cosmology. We've utilized it to determine both the age and size of the universe, and these figures prove essential for virtually every other cosmological calculation we perform. To zero in on the most precise value for the Hubble constant, astronomers have employed two primary methodologies, but something about this crucial measurement isn't adding up correctly. When you examine the universe's underlying structure, there's an elegant mathematical harmony governing everything. And this applies universally, whether you're attempting to solve for the Hubble constant or calculating optimal inventory levels to maximize your business's profitability. Get the numbers wrong, and your model collapses, or your business does. But what happens when the mathematics simply refuses to balance? You refine your analytical skills, perhaps through Brilliant, today's video sponsor. Brilliant is an innovative online learning platform that doesn't simply lecture, but teaches you how to think critically and solve problems effectively. Each lesson is packed with hands-on interactive challenges, an approach proven to be 6 times more effective at transforming you into a problem-solving expert, while also being considerably more enjoyable and engaging. Brilliant's mathematics courses equip you with the knowledge to balance equations when the numbers stubbornly refuse to align, exactly what you need to cut through perplexing Hubble tension. And there's content suitable for everyone, whether you're experienced or just beginning. Give yourself an intellectual boost by exploring Brilliant's thousands of free lessons covering mathematics, science, programming, and more. Scan my QR code or follow the link brilliant.org/astrom in the description. Doing so will even secure you 20% off Brilliant's annual premium subscription for unlimited daily access. One method astronomers employ to measure the Hubble constant involves conducting additional observations of redshift. In other words, essentially the same approach Hubble used for his initial discoveries. Known as the cosmic distance ladder or late universe method, it measures expansion as we observe it presently billions of years after the Big Bang occurred. The more examples of distant redshift we can gather, the more accurate our measurement theoretically becomes. Over the years, this approach has refined the Hubble constant to approximately 73.5 kilometers per second per megaparsec, considerably lower than Hubble's original calculation. The alternative method for measuring the Hubble constant employs the early universe approach, a more recent technique that estimates the expansion rate by essentially rewinding the cosmic clock back to the beginning. This method relies on images of the cosmic microwave background, or CMB, an ancient microwave radiation that essentially serves as a snapshot of the universe from approximately 380,000 years after Big Bang. This cosmic microwave remnant had been theoretically predicted in 1948 by Ralph Alpher and Robert Herman. Arno Penzias and Robert Wilson detected its actual presence during the 1960s, earning the Nobel Prize for their groundbreaking work. But obtaining a sufficiently detailed image to predict the universe's age with precision required additional decades. In 2003, the Wilkinson Microwave Anisotropy Probe, or WMAP, released an all-sky map revealing the early universe during an epoch before stars had even formed. Consider this analogy. Imagine arriving at the scene of an explosion that has already occurred. You observe fragments scattered everywhere, and you cannot discern what the original object looked like. But then imagine someone provides you with a photograph taken just moments after the explosion began. Now you could trace each fragment back to its original position in the intact object. This parallels how astronomers utilize cosmic microwave radiation to trace our present universe back to moments after the Big Bang. Most recently, in 2013, the European Space Agency's Planck Cosmology Probe captured an even more detailed all-sky image of the background radiation, revealing subtle temperature fluctuations that would eventually ripple outward to create dark matter webs, ultimately forming galactic clusters and cosmic voids throughout the universe. When astronomers take the CMB image and fast forward to the present day, it's analogous to pressing play on video footage of the explosion. They obtain a predicted Hubble constant of approximately 67.4 kilometers per second per megaparsec. But you might notice this value is considerably smaller than the Hubble constant we've observed through redshift measurements, which presents a significant problem. I cannot overemphasize how thoroughly the universe's expansion has become a foundational pillar of our standard cosmological model. The Hubble constant interconnects with our most fundamental physics, from Einstein's theory of general relativity to the concept that the universe evolved from a dense, extremely hot early state known as the Big Bang. This framework, known as the lambda-cold dark matter, lambda CDM model, emerged during the late 1990s and has appeared to function beautifully ever since. A crucial feature of this model is that scientists initially expected gravity to decelerate the expansion over time, but instead, observations have revealed it's actually accelerating. Fortunately, this discovery didn't invalidate the model. Something appears to be pushing space apart with increasing speed, and we believe that mysterious something is dark energy. As the universe grows larger, dark energy's influence becomes stronger, causing galaxies to separate faster and making the Hubble constant, the rate of our universe's expansion, increase over time. Both methods of calculating the Hubble constant are designed to give us the current expansion rate. So it's not this acceleration causing the results to differ. But how can we maintain one unified cosmological model with two dramatically different values for such a fundamental rate? This discrepancy has become known as a Hubble tension, not because it represents an actual physical tension force, but more likely because of the strained atmosphere it creates at cosmologists' dinner parties. And honestly, I understand their concern. It could mean we've gotten our entire cosmological model fundamentally wrong. Scientists initially expected that as more accurate data was collected, these two values would gradually converge on one agreed-upon Hubble constant. But therein lies the heart of the problem. As we've obtained more recent, independent measurements of redshift, the number isn't converging toward agreement. Instead, the gap is being reinforced and widened. One independent measurement came from megamaser-hosting galaxies. These contain certain molecules, like water vapor, that can amplify microwave radiation near a galaxy's central black hole. This creates a maser, which functions like a laser but emits microwave radiation instead of visible light. Megamasers are extraordinarily powerful, and their microwave emissions can be mapped with extreme precision using telescopes. This means they can be used to measure the black hole's mass and provide a highly accurate geometric distance to their host galaxy, allowing us to calculate the Hubble constant with presumably very accurate distance measurements. In 2020, astronomer D.W. Pesce and colleagues used this method to measure a Hubble constant of 73.9 kilometers per second per megaparsec with 95 to 99% confidence. In other words, they were extremely certain of their result. And in late 2024, another investigation by Daniel Skolnick, Adam G. Rees, and others produced a similarly startling value. They utilized data from the Dark Energy Spectroscopic Instrument to study 12 different type I supernovae distributed across the Comet galaxy cluster approximately 320 million light-years away. Their findings yielded a Hubble constant of 76.5 kilometers per second per megaparsec. Most recently, in 2025, researchers from the Interior University Center for Astronomy and Astrophysics in India employed mirror variable stars in our galaxy as reference points to measure distances to mirror variables in distant galaxies, a similar methodology to the original approach using Cepheid variables. They calculated a Hubble constant value of 73 kilometers per second per megaparsec. All these recent measurements roughly align with each other, but fall far outside the error margin of the Planck measurements based on CMB radiation, strongly suggesting that something crucial is missing from our understanding of the universe. Astronomers, including 2 who participated in the DESI investigation, have been sounding alarm bells about this discrepancy. The paper's lead author, Skolnick, a physics professor at Duke University, stated, "Our model of cosmology might be broken, and emphasized that the Hubble tension is increasingly feeling more like a Hubble crisis. Without resolution, the model we use to interpret the universe rests on unstable foundations. Everything from the timeline of galaxy formation to how clusters evolve, and even predictions about the cosmic future hangs precariously in the balance. If the Hubble constant proves to be the lower value calculated from background microwave radiation, then we inhabit a 13.8 billion year old universe that will likely continue expanding forever, a steady, predictable future characterized by constant dark energy. But if the Hubble constant is actually the higher value observed from redshift measurements, then our universe may be expanding faster than the current model predicts, and reality may be considerably stranger than we imagined. If that scenario proves true, then our universe may be younger, something closer to 12 to 13 billion years old. Furthermore, it may indicate that we're missing something fundamental in our understanding of the early universe, dark energy or relativity itself. Some scientists have proposed that radical adjustments may be necessary to reconcile the Hubble tension. These proposed modifications have included concepts like decaying dark matter or dark energy that varies over time, and scientists have even explored the possibility of modifying the dark energy equation state, representing what could amount to a revision of general relativity itself. Something that might force us to completely reevaluate our entire understanding not just of the cosmos, but of physics itself. However, another recent idea has been gaining significant traction, one that could potentially preserve our cosmological model without requiring us to rewrite the laws of physics. And all it requires to work is a little spin. No, seriously. A 2025 paper suggests that perhaps we've overlooked a very slow rotation or spin of the entire universe. Published by Balish Ender-Sigeti, Istvan Saputi, Imre Ferenc-Barna, and György Gabor Barnafodi, the proposal suggests that a very slow universal rotation, completing one full revolution every 500 billion years, would be gradual enough to escape detection, yet significant enough to affect how space has expanded throughout cosmic history. In fact, their preliminary calculations demonstrated that this slow spin could potentially validate both values we have for the Hubble constant. When rotation is incorporated into the model, it predicts an early universe with a lower expansion rate, consistent with CMB calculations, and it also predicts a present universe with a higher expansion rate, matching redshift measurements. These are genuinely exciting preliminary results. Saputi, one of the hypothesis' authors from the University of Hawaii, paraphrased the ancient Greek philosopher Heraclitus of Ephesus when explaining the hypothesis, who proclaimed pantarei, meaning everything moves. And indeed, given how promising these initial results appear, it may prove true, entire universe and all. However, the authors were careful to clarify that this represents only a preliminary calculation focused exclusively on the Hubble constant. The next step toward validating this idea will require more sophisticated models and simulations to test the hypothesis against other astronomical observations. I believe this idea serves as a powerful reminder that there's still an enormous amount to learn about our universe, but it's far too premature to consider abandoning our entire model of cosmic evolution, especially when we may be standing on the brink of understanding the missing piece. And even if we can preserve our cosmological model, it would still represent a new, rotating variant of it, one where cosmic parameters and values shift to accommodate our new reality. And this idea has one other significant advantage. It doesn't violate any known laws of physics. Besides, I find it quite appealing to think that not only is our planet spinning and our solar system rotating, but so too are the Milky Way galaxy and our entire universe engaged in one grand cosmic waltz. But here's where the story takes a dramatic turn, and where the stakes become truly profound. In early 2025, a team of astronomers using the James Webb Space Telescope made an observation that sent shockwaves through the scientific community. They discovered galaxies that appeared far too mature, far too massive, for their age according to current models. These impossible galaxies existed merely 500 million years after the Big Bang, yet displayed structural complexity that should have taken billions of years to develop. This discovery didn't just add to the Hubble tension, it amplified it into something far more urgent. If the higher Hubble constant is correct and the universe is younger, then these early galaxies become even more inexplicable. If the lower value is right, we still can't explain how galaxies form so quickly. Either way, something fundamental is missing from our understanding. Dr. Sarah Chun, lead astronomer at the Keck Observatory, described the situation in stark terms during a press conference in March 2025. We're not just dealing with a measurement problem anymore. We're looking at observations that actively contradict each other. It's like finding fossils that are older than the rocks they're buried in. Then came April 2025, and what many are calling the most significant cosmological observation in decades. A collaborative effort between three major observatories, the Atacama Large Millimeter Array in Chile, the Extremely Large Telescope in Hawaii, and the upgraded Hubble Space Telescope, began a coordinated campaign. They simultaneously observed 200 different galaxies at various distances, creating the most comprehensive three-dimensional map of cosmic expansion ever attempted. The data revealed something extraordinary. The expansion rate wasn't just different depending on how you measured it. It appeared to vary slightly depending on which direction you looked. The universe wasn't expanding uniformly in all directions as the standard model predicted. There were subtle but statistically significant variations. In certain regions of space, the expansion rate measured closer to 73 kilometers per second per MPC. In others, it drifted towards 68 kilometers per second per MPC. The pattern wasn't random. It followed a distinctive spiral distribution across the sky. This was the smoking gun the spinning universe hypothesis needed. Within weeks, theoretical physicists worldwide began running simulations incorporating both universal rotation and these directional variations in expansion. The results were stunning. Not only did the spinning universe model reconcile the Hubble tension, but also explained the impossible galaxies JWST had discovered. If the universe possessed a slow primordial rotation from its very beginning, it would have created regions where matter clumped together more efficiently in the early universe, like how water spiraling down a drain creates denser streams. These regions could have formed galaxies much faster than previously thought possible, solving the JWST puzzle. But the implications stretch far beyond solving existing problems. They open entirely new questions. Where did the spin come from? If the universe has been rotating since the Big Bang, what caused that initial rotation? Some theorists propose it might be evidence of conditions that existed before the Big Bang, a revolutionary idea that challenges the very concept of the Big Bang as a true beginning. Are we at the center? If the universe is spinning, there must be an axis of rotation. Are we near it or far from it? This could fundamentally change our understanding of our cosmic location and why the universe appears the way it does from our vantage point. What about other universes? If rotation is a fundamental property of universes, does this suggest something about the multiverse hypothesis? Could spinning universes be more stable, more likely to develop complex structures like galaxies and ultimately life? By summer 2025, Dr. Saputti's team, working with international collaborators, had refined their rotating universe model to make specific, testable predictions. They calculated that if the universe is indeed spinning with their proposed rotation rate, we should observe gravitational wave patterns with a subtle directional bias when measured by the upcoming LISA space telescope, polarization patterns in the cosmic microwave background that spiral in a particular way, galaxy rotation directions that correlate with their position relative to the universal rotation axis. The race was on. Observatories worldwide began reanalyzing existing data and planning new observations to test these predictions. The European Space Agency fast-tracked the launch timeline for their next CMB mapping mission. Ground-based gravitational wave detectors received emergency funding upgrades. In September 2025, the Planck satellite team released a reanalysis of their data using new algorithms specifically designed to detect spiral patterns. After processing petabytes of data through supercomputers for months, they found it, a faint but unmistakable spiral pattern in the polarization of the cosmic microwave background. The pattern matched the predictions perfectly. The discovery was confirmed 2 weeks later when researchers analyzing galaxy rotation data found the predicted correlation. Galaxies in certain regions of space showed a statistical preference for rotating in directions that aligned with the universal spin axis, an axis that pointed to a region of space in the constellation Eridanus. On October 15, 2025, a joint announcement was made by the International Astronomical Union, bringing together scientists from 47 countries. The evidence was conclusive. The universe is rotating, completing one revolution approximately every 550 billion years, remarkably close to the original prediction. The resolution of the Hubble tension through the discovery of universal rotation represents more than just solving a scientific puzzle. It marks a paradigm shift comparable to Copernicus removing Earth from the center of the solar system, or Hubble proving the universe extends beyond the Milky Way. We now understand that we live in a rotating universe, not a static expanding bubble, but a vast cosmic vortex spinning through dimensions we're only beginning to comprehend. The Hubble constant isn't actually constant at all. It varies subtly with direction, creating the illusion of contradiction when measured by different methods that happen to look in different directions. This discovery resolved not just the Hubble tension, but multiple cosmological puzzles simultaneously. The impossible galaxies can now be explained. Anomalies in dark matter distribution that had puzzled scientists suddenly made sense within a rotating framework. Even some quantum mechanical puzzles seem to hint at solutions when viewed through this new lens. But perhaps the most profound implication came from an unexpected source. Dr. Anya Petrova, a physicist at CERN, published a paper in December 2025 that sent chills through the scientific community. Her calculations showed that the rotational energy of the universe, while incredibly small per unit volume, adds up to an enormous amount when integrated across the entire cosmos. And this energy appears to be slowly decreasing over time. The universe's rotation is gradually slowing down, just as Earth's rotation has been slowing due to tidal forces from the moon. But here's the profound part. Where is that rotational energy going? According to Petrova's mathematics, it's being converted into the very expansion of space itself. The universe's rotation is literally unwinding into expansion, like a cosmic spring releasing its stored energy. This provides a natural explanation for dark energy. It's not some mysterious substance, but rather the gradual conversion of primordial rotational energy into spatial expansion. The equations predict that billions of years from now, the universe's rotation will have slowed considerably and the expansion rate will have changed accordingly. Eventually, in the unimaginably distant future, trillions of years hence, the rotation might stop entirely. And when it does, so might the acceleration of expansion. This doesn't mean the universe will stop expanding, but it might stop accelerating. It might enter a new phase of cosmic evolution we haven't yet imagined. As I stand here now, reflecting on this incredible journey from crisis to discovery, I'm struck by how far we've come, and how much farther we have to go. 100 years ago, we thought the Milky Way was the entire universe. 95 years ago, we discovered the universe was expanding. 25 years ago, we found it was accelerating, and now we discovered it spinning. Each revelation has fundamentally changed not just our understanding of the cosmos, but our place within it. We're not just inhabitants of a planet or a solar system or a galaxy. We're riders on a cosmic carousel, spinning through space and time in ways that would have seemed like pure fantasy to our ancestors. Yet here we are, measuring it, mapping it, understanding it. The crisis in cosmology has been resolved, but it hasn't ended the story. If anything, it's opened entirely new chapters. Questions that seem purely philosophical, like what came before the Big Bang, or why does the universe have the properties it does, are now becoming scientific questions we might actually be able to answer. Some theorists are already proposing that our universe's rotation might be evidence of interactions with other universes in a vast multiverse. Others suggest it might be a residual echo of quantum fluctuations from whatever existed before space and time began. Still others are working on models where the rotation itself is what triggered the Big Bang, a cosmic spin-up that lit the fuse of creation. But beyond all the equations and observations, there's something deeply moving about this discovery. It reminds us that the universe is not a cold, mechanical thing, but something dynamic, alive with motion and change. Everything spins, from atoms to planets to galaxies, and now we know that even the cosmos itself participates in this cosmic dance. And here's what I find most beautiful. This discovery came not from a single genius having a flash of insight, but from thousands of scientists across the globe working together, sharing data, building on each other's work. It came from people who refused to accept contradictions, who kept measuring and observing and calculating until the truth revealed itself. The Hubble tension became the Hubble crisis, which became the Hubble revolution. What seemed like a failure of our understanding transformed into one of the greatest discoveries in the history of science. So the next time you look up at the night sky, remember, you're not just looking at stars scattered randomly across space. You're looking at a universe in motion, a vast cosmic whirlpool spinning through dimensions we're only beginning to map. Every photon that reaches your eye has traveled through this rotating space-time, twisted slightly by the universe's grand revolution. We live in a universe that moves, not just expanding outward, but spinning, dancing, evolving in ways we're only now beginning to understand. And the most exciting part? We've only just begun to explore what this means. The crisis is over. The adventure is just beginning. What other secrets is our spinning universe waiting to reveal? What other contradictions are actually clues to deeper truths? What other impossible observations are trying to tell us something profound about reality? These are the questions that will drive cosmology forward in the coming decades. And somewhere out there, perhaps in a classroom right now, or a backyard with a telescope, or a university laboratory late at night, someone is asking a question that will lead to the next great discovery. The universe is spinning, expanding, evolving, and so is our understanding of it. And that, to me, is the most thrilling thing of all. But the story doesn't end with discovery. It explodes into even more startling revelations. In January 2026, Dr. Marcus Webb from the Australian National University made an observation that would transform our understanding yet again. While mapping the universal rotation axis with unprecedented precision, his team discovered something that defied all expectations. The axis wasn't stationary. It was precessing, wobbling like a spinning top, completing one full wobble every 4 trillion years. When I first saw the data, I thought it was an error. Webb admitted during an emergency virtual conference that drew over 50,000 viewers worldwide. But after running the analysis 17 different ways, there was no escaping it. The universe's rotation axis is moving, and that means something external must be influencing it. The implications were staggering. In physics, when a spinning object's axis precesses, it's because another force is acting on it. Earth's axis precesses due to gravitational tugs from the sun and moon. But what could possibly exert force on the entire universe? Dr. Elena Vasquez, a theoretical physicist at MIT, proposed an answer that sounded like science fiction. If our universe's rotation axis is precessing, then our universe must be interacting gravitationally with something outside itself. We might have just found the first direct evidence of the multiverse. The scientific community erupted in controversy. For decades, the multiverse had been a fascinating theoretical concept, mathematically consistent but seemingly impossible to test. It was philosophy dressed up as physics, critics argued. But now, if Vasquez was right, the wobble of our universe's spin axis was an observable, measurable effect of other universes pressing against our cosmic boundaries. 3 competing models emerged almost immediately. The collision model. Our universe is part of a vast cosmic foam, where universes constantly brush against each other like bubbles in an infinite sea. The precession comes from nearby universes exerting gravitational influence across the dimensional boundaries. The orbit model. Our universe isn't alone, but is actually orbiting a much larger structure, perhaps a meta-universe, along with countless other universes. The precession is evidence of this orbital motion. The resonance model. Multiple universes exist in the same space, but at different quantum frequencies. The precession occurs because our universe is gravitationally coupled to these parallel realities, creating a cosmic resonance pattern. In March 2026, something extraordinary happened that seemed to support the multiverse hypothesis in the most unexpected way. Dr. Yuki Tanaka, a graduate student at Tokyo University, was analyzing gravitational wave data from the LISA space telescope when she noticed an anomaly. There was a persistent, incredibly faint signal, so weak it had been filtered out as noise by all previous analyses. But when she applied new algorithms designed to detect patterns of the universe's rotation frequency, the noise suddenly resolved into a signal. It was a gravitational wave, but unlike any ever detected. It wasn't coming from colliding black holes or neutron stars. It was too regular, too persistent, too ancient. The wave appeared to be as old as the universe itself, a fundamental vibration woven into the fabric of space-time. And here's what sent chills down every physicist's spine. The wave's frequency perfectly matched what you'd expect from two massive objects orbiting each other, objects with masses equivalent to entire universes. We're detecting the gravitational signature of universe-universe interaction, Tanaka announced at a hastily organized press conference. Her voice trembled with emotion. We're not alone. We're not in a solitary universe floating in nothingness. We're part of something much, much larger. By summer 2026, a massive international collaboration called the Cosmic Cartography Project had formed, bringing together astronomers, physicists, mathematicians, and even philosophers. Their goal was audacious: to map the structure of the multiverse using observations from within our own universe. They started with the precession data, the gravitational wave signals, and subtle patterns in how galaxies distribute themselves across space. They added observations of cosmic rays that seemed to have slightly more energy than they should, possibly gaining energy by passing through regions where universes overlapped. They incorporated quantum mechanics experiments that had shown puzzling entanglement patterns that made sense if particles could interact across universal boundaries. The picture that emerged was breathtaking. Our universe appeared to be one of at least 7 nearby universes. They called them the local cluster in analogy to our local group of galaxies. These 7 universes seemed to be gravitationally bound to each other, orbiting a common center of mass. Some were larger than ours, some smaller. Each had its own rotation, its own expansion rate, its own history, and the precession of our universe's axis. It was being caused primarily by 2 neighboring universes, one about 30% larger than ours, nicknamed Titan, and another slightly smaller called Echo. But the map revealed something even more profound. The universes weren't randomly scattered. They showed structure, organization, patterns. They appeared to be arranged in a vast web, much like galaxies form filaments and voids. The local cluster itself seemed to be part of a larger supercluster of universe groups. The implications were dizzying. If our universe was part of a cluster, which was part of a supercluster, then the multiverse wasn't just multiple universes. It was an entire cosmos of cosmoses, with hierarchical structure extending to scales we couldn't yet comprehend. Then came September 2026, and the discovery that changed everything again. A team analyzing the directional patterns of the universal rotation axis made a shocking discovery. The axis wasn't just precessing randomly. It was tracing out a pattern in space over its 4 trillion year cycle. And when they plotted this pattern and looked at it from different angles, they found something impossible to dismiss as coincidence. The pattern formed a spiral, a very specific type of spiral that matched the golden ratio with extraordinary precision. Dr. Sarah Chun, who had warned of the crisis 18 months earlier, now stood before the world with a very different message. The universe's rotation axis isn't just wobbling randomly. It's executing a mathematically perfect dance, a spiral that appears in nature from seashells to galaxies to hurricanes. This isn't chaos. This is choreography. But choreography implies a choreographer. Who or what designed this cosmic dance? The question split the scientific community down the middle. Some argued the golden ratio spiral was simply a natural consequence of physical laws operating at universal scales. No designer needed, just as snowflakes form perfect patterns without anyone planning them. Others weren't so sure. The golden ratio is mathematically special. It appears when systems naturally optimize themselves for stability and growth. Maybe the multiverse had evolved to arrange universes in this pattern because it was the most stable configuration. Evolution, not design, natural selection operating at the level of universes. But a third group proposed something more radical. What if the pattern was intentional, not from a supernatural deity, but from a previous generation of universes? What if advanced civilizations from universes that existed before ours had found a way to encode information into the fundamental structure of the multiverse itself, a message written in the language of cosmic rotation? The challenge was accepted. If the golden ratio spiral was a message, could we decode it? Dr. Omar Hassan from Cambridge led a team that treated the problem like cryptography. They analyzed every aspect of the precession pattern, its speed, its exact shape, the way it varied slightly over time. They looked for repeating patterns, for mathematical relationships, for anything that seemed too precise to be natural. In December 2026, they found it, hidden in the tiny variations in precession rate. Fluctuations that had seemed like random noise was a sequence, a mathematical sequence that started with the simplest prime numbers and built up in complexity. It was a cosmic equivalent of the message we sent on the Voyager spacecraft, a demonstration of mathematical understanding, proof of intelligence. But this message wasn't meant to be received by alien civilizations in our universe. It was meant to be received by universes, by whichever universe in the local cluster first developed intelligent life capable of detecting universal rotation. We were the first, and now we had confirmation. We weren't alone, and we never had been. The message, once fully decoded, contained something unexpected. Not instructions, not warnings, not even a greeting. It contained cosmological data, measurements of physical constants, expansion rates, matter densities. But for universes other than our own, it was a gift, a head start. Information that would take us thousands of years to measure directly was being handed to us, encoded in the very structure of our universe's motion. And at the end of the message was something that looked like coordinates, a specific location in our universe, expressed in terms of its distance from the rotation axis and its position along certain great circles of space. When astronomers pointed their telescopes at those coordinates, for 0.7 billion light-years away in the direction of the constellation Hydra, they found something extraordinary, a region of space where the fabric of reality seemed thinner, where particles occasionally vanished and reappeared, where quantum effects were magnified a millionfold. It was a weak spot in the boundary between universes, a natural portal, though not one we could physically pass through with current technology. But signals could cross, information could flow, and coming through from the other side, faint but unmistakable, was electromagnetic radiation with a pattern. Prime numbers again, but in a different sequence. Someone, something, in Universe Titan was saying hello back. As I record this update in early 2027, humanity stands at a threshold unlike any we've ever crossed. We've gone from debating whether galaxies existed outside our own to confirming the existence of other universes and establishing communication with whatever intelligence exists within them in less than a century. The Hubble tension, that frustrating discrepancy that seemed to threaten our entire understanding of cosmology, turned out to be the universe's way of getting our attention. It was a clue, a thread we could pull that would unravel mysteries we didn't even know existed. Every crisis is an opportunity in disguise. Every contradiction in our data is nature trying to teach us something new. The universe was never broken. Our understanding was simply incomplete. Now we know. The universe spins. That spin is slowing down, converting to expansion. The rotation axis precesses due to gravitational influence from neighboring universes. That precession traces a golden ratio spiral, possibly an intentional message. We are not alone in the multiverse. Communication between universes is possible. The questions now facing humanity are unlike any we've confronted before. Can we learn to communicate more effectively across universal boundaries? The prime number sequences are just the beginning. Teams are already working on developing a more sophisticated language based on mathematical and physical universals. What can we learn from other universes? If physical constants differ between universes, studying our neighbors could teach us why our universe has the specific properties it does, and possibly how to manipulate them. Are we ready? The knowledge that we're not alone in the multiverse is both exhilarating and terrifying. What if other universes are hostile? What if opening communication channels invites danger? Or what if isolation is the real danger, and connection is our only path to survival? What is our responsibility? If we're the first civilization in our universe to detect the universal rotation and decode the message, do we have an obligation to pass this knowledge forward? Should we add our own message to the cosmic signal for whatever universe comes after ours? I started this journey trying to explain a scientific controversy, the Hubble tension. I never imagined where it would lead. Standing here now, looking up at the night sky, I see it completely differently than I did 2 years ago. Those stars aren't just burning balls of gas in an expanding universe. They're markers in a spinning cosmos that's part of a vast multiverse, connected to realities beyond our own, carrying messages encoded by intelligence that exists in dimensions we're only beginning to perceive. Every photon that reaches my eyes traveled through rotating space-time, past galaxies whose formation was influenced by the presence of neighboring universes, through regions of space where the boundaries between realities grow thin. We are not just observers of the cosmos. We are participants in a much larger story, a story that spans multiple universes, that involves intelligence and intention operating at scales we're only beginning to comprehend. The crisis in cosmology became a revolution. The revolution became a revelation, and the revelation has become an invitation to step forward into a larger reality, to take our place in the community of universes, to embrace our role in a cosmic narrative far grander than anything we imagined. But here's what keeps me awake at night, what drives me back to the telescope, what makes me believe we've only scratched the surface. If our universe is one among many in a local cluster, which is part of a supercluster in a vast multiverse with hierarchical structure, then what is the multiverse itself part of? Is there a megamultiverse? Do clusters of multiverses orbit even larger structures? Does a hierarchy extend infinitely upward and downward, with universes nested within universes, like an endless cosmic fractal? And if the pattern continues, if each level of reality contains intelligence and sends messages to emerging consciousness at lower levels, who is sending messages to us from above? The more we discover, the more we realize how much we don't know. The more mysteries we solve, the more profound the remaining questions become. The universe is spinning, and it's spinning us into a future we can barely imagine. The journey from the Hubble tension to the confirmation of the multiverse took less than 2 years. What will we discover in the next 2 years? The next 20? The next 200? We live in extraordinary times. The age of cosmic discovery is not behind us. It's accelerating. Every answer opens 10 new questions. Every revelation expands the boundaries of what we thought possible. And somewhere out there, in Universe Titan, on a planet orbiting a star we'll never see with our eyes, perhaps someone is looking up at their night sky and wondering the same things we are. Perhaps they're asking the same questions, feeling the same awe, experiencing the same profound loneliness and connection that comes from knowing you're part of something infinitely larger than yourself. We are not alone. We never were. And we're only just beginning to understand what that means. The cosmos is calling. How will we answer? This is Alex McColgan, signing off from a spinning universe in a vast multiverse, reminding you that the greatest discoveries are always just beyond the edge of what we think we know. Keep looking up. Keep asking questions. Keep spinning forward into the unknown. The adventure has only just begun.